Check out this animation showing two helium atoms approaching one another. The meter on the right shows the kinetic energy and the total energy of the system at a particular instant. The line graph above the atoms represents the potential energy of the system. Atoms start at a distance where they just start to experience the interactions, but as they get closer, you may notice that there are changes to the kinetic and potential energies of the system. Let's begin today by thinking about what happens to the potential energy of the system as the atoms come together. If you want to explore this phenomenon further, check out the simulation that's linked to this video. As we consider this system of two helium atoms, remember the electrostatic interactions present. The electrons of each helium atom are attracted to the nucleus of the other atom. This attraction is what initially causes the kinetic energy to increase as the atoms gain velocity and the potential energy to decrease as the atoms get closer to one another. Notice, though, that as the atoms move closer to one another, the total energy of the system remains constant. Eventually, the atoms get too close to one another, and the electrons from each atom start to repel each other, causing a sharp increase in the potential energy. Because of the repulsion, the atoms move away from each other, and the kinetic energy increases. In this way, electrostatics cause the attraction that moves the atoms towards one another, and the repulsion, pushing them apart. This is a closed system, so the total energy is constant. If we leave it alone, it will oscillate forever. But that's not really realistic, since we don't have isolated systems like this out in the real world. Now let's reflect on the potential energy curve as the two helium atoms approach one another. What happens to the potential energy of the system as the atoms approach one another? Do you think it'll increase, decrease, or stay the same? In this case, the potential energy would decrease. If this is surprising, check out the GIF presented earlier in the video to explore this a little further. Now consider what happens to the potential energy as the atoms get very, very close to each other. Again, do you think that the potential energy will increase, decrease, or stay the same? The potential energy should increase, since the like charges between electrons on each helium should begin to repel one another. Presented here is a potential energy curve for two atoms approaching one another. Let's think about the forces the atoms will experience at various points on the curve. We're going to start on the very right side. When the atoms are a far distance apart and they move closer together, which force is the strongest? At this point in the graph, the electrostatic attraction between the atoms is the strongest. However, if we move to the bottom of the curve, when the potential energy is at a minimum, which force is the strongest? The answer here is D. The electromagnetic attraction and repulsion are equal. Consider what's happening with the atoms here. If they get any closer, then the repulsion is larger, but if the atoms get any further apart, the repulsion is weakened, leaving room for the attractive forces to bring the atoms together. Finally, what is the nature of the force when the atoms are very close together? We sort of talked about this one in the last question on this graph. The atoms are repelled from one another because of the like charges of each's electron clouds. So if we took another look at the atoms moving along this graph from right to left, the atoms initially move closer because of the attractive force. In this part of the graph, kinetic energy is increasing as potential energy decreases. At the bottom of the potential energy well here, there will be some vibration, but the atoms will stick together for the most part. This represents a stable system, and energy is needed to break interactions if the system of two atoms is going to change from the potential energy well, since the attractive forces equal the repulsive forces. Finally, at the very top left of the potential energy diagram, the atoms are very close to one another. At this part of the graph, the two atoms are strongly repelling one another because of the overlap of their electron clouds. Now let's think about what the depth of the potential energy well can tell us. What do you think the point at the very bottom of the potential energy diagram communicates? The answer here is B. Notice that the y-axis is labeled as potential energy. The depth of the well must therefore be an amount of energy. Since the potential energy of the system is at its lowest, the system would need to gain energy to break the interactions between the atoms. That is, the depth of the well tells us how much energy must be required to push the atoms closer or further apart. Now let's think about the other axis. What does the position of the x-axis of the potential energy diagram tell you? The x-axis tells you the internuclear distance, or you can picture this as how far apart the atoms are from one another. The location of the x-axis that aligns with the lowest point on the potential energy diagram communicates how far apart the atoms are when they are at their most stable distance. Here we have three different distances between helium atoms. Could you position them on the curve we are analyzing? Take a moment to pause the video and try and place these sets of atoms where they belong on the potential energy diagram, using the labels for locations A, B, and C. At position C, the distance between the atoms would be the highest. This would represent the first picture. In the second picture, the electron clouds are right on top of each other and overlapping. The repulsive force between the electrons would increase the potential energy, so it should be location A on the curve. The third image has the two electron clouds at an intermediate distance apart. This is the most likely candidate for the potential energy minimum, so it would most likely correspond to the position B on the curve. Let's take a quick moment to review. We watched an animation of two helium atoms approaching one another. When they first start to approach one another, it looks like the image shown here. When they first come together, the potential energy starts to drop, and kinetic energy starts to increase. When they get too close, the potential energy spikes as the atoms repel one another. Total energy never changes because this is an isolated system. Atoms are just bouncing back and forth. When helium atoms are within a range of each other, an electrostatic force exists that attracts them together. Eventually, the atoms get too close and are repelled by one another. The atoms then move apart until the attractive forces take over again. In a closed, isolated system, this oscillation would continue forever if more energy is not introduced to the system. Now that we've reviewed, try these questions. Go ahead and pause the video again to give them a try. Quickly working through these, the answer to number 1 is that the total energy still won't change because we have an isolated system. Number 2, the kinetic energy is high, but it decreases as the electron cloud starts to overlap and the atoms slow down. Once they begin to move apart again, it will increase again. And question 3, what happens to the potential energy? The potential energy increases sharply because of the repulsion between the electron clouds of each atom. Let's take one last look at the potential energy diagram to consider why do the helium atoms stay in this energy well. Essentially, the atoms do not stay at the potential energy minimum because they have too much energy. This is similar to a ball rolling down a hill. If there is enough energy, the ball will roll back out the other side of the hill. We'll wrap things up today with one last set of review questions. These are the same questions as last time, but now the atoms are very, very close to one another. Take a moment to consider how you would respond to each of these 3 questions. Again, what happens to the total energy, the kinetic energy, and the potential energy? The answers here would be to number 1, what happens to the total energy? The total energy still won't change. Remember, this is an isolated system, and it's not necessarily exactly what we would see in nature, but it works well for describing this system of two helium atoms approaching one another. Number 2, what happens to the kinetic energy? The kinetic energy was high, but decreases as the electron clouds start to overlap and the atoms slow down. Once they begin to move apart, it will increase again. So, as the electron clouds begin to overlap, the atoms will lose kinetic energy because they'll slow down. But they will gain kinetic energy as the repulsive forces push these atoms apart from one another. And finally, our third question, what happens to the potential energy? Well, the potential energy would increase sharply because of the repulsion between the electron clouds of each of these two helium atoms. However, remember that the potential energy will decrease, again, as the atoms begin to slowly start moving apart, as we discussed in our answer to number 2. If you'd like, remember to check out the simulation linked with this video, which explores the relationship between the energy of a system and two atoms approaching one another.